So what do these folks do? They basically are very worried about the U term, researcher degrees of freedom. In other words, once you have data in hand, stuff you can do to make an effect significant, that is really a null effect. That's really a zero. And that leads them to believe that for any given research study that they read, they're pretty skeptical about whether it's a real effect. So this is their main table. And they're interested in the likelihood of obtaining a false positive. So this is just 1 minus the PPV. The PPV is like, what are the odds that, like, when I see a result, it's real? And, this is sort of the opposite. Like, when I see a result, it's not exactly, but, when I see a result, is it a false positive, basically? So kind of like 1 minus the PPV. The wording isn't exactly the same. The denominators are different in those two, but let's just say it's roughly 1 minus PPV. And they look at researcher degrees of freedom in 4 cases, which are listed out here. Now remember, this data is pure noise. They've generated noise. So anything, and we're going to focus on this p less than 0.05 column. So standard levels of significance. Given that it's noise, the chance that we reject the null for all of these cases should be exactly or close to 0.05. Other than some sampling variation. If it was 0.04, I'd be happy. If it was 0.06, I'd be happy. But it shouldn't deviate much from 0.05. So what are the different cases that they look at? The first is, what if you just had 2 outcome variables? Okay? Very typical situation when you're, say, doing field work or you're in the lab. You collect a couple different measures of the same thing. And they say, what is the researcher degrees of freedom here? They're actually going to allow these things to be pretty highly correlated. They're not just noise. They're 2 correlated measures at 0.5 of the same thing. If I can focus on one as my main outcome and sort of ignore the other, if I can focus on measure B rather than measure A, or if I can take the average of the 2, those are the 3 things I can do with the data. If I can do those 3 things with these highly correlated outcome measures, I've doubled the chance I can reject the null. Case 2, and this is really, again, this is where we're more in like the lab world. Can I collect 10 more observations for a given cell? So I'm in the lab. I'm looking at my data as it comes in. I'm like, ooh, this is looking pretty interesting. I want a little more data for treatment 2. I think that one's kind of interesting. If I can do that and get 10 more observations per cell, just 10 more observations, I'm already from 5 to 8%. And apparently, and he has some data in the paper here, 70% of lab social psychologists do this. They kind of look at their data and decide which treatments to get more data for. So already, we can't really believe p-values there. 3 is really another useful one. What if I just have one covariate, gender? And again, this is like, it's correlated with the outcomes through chance here. It's all noise. What if I have one covariate, so I can either control for the covariate or not, or I can focus on the interaction between treatment and the covariate, basically look at subgroups. Those are the things I can do. Will any of those yield a p, greater than 0.05? I'm at 11.7%. Just one covariate. People have dozens or hundreds of covariates. Okay, and then the last one here is, there were 3 experimental conditions. What if I can just sort of exclude the data from one of them and sort of not report it? Just say, oh, that treatment didn't work. And that happens all the time. Again, in field experiments and lab experiments, people say, oh, that just didn't kind of work. Again, I have a much higher p-value. So any of these very limited things, 10 observations, 1 covariate, 2 outcomes, lead to misleading p-values. But what gets really scary in this exercise is the ability to combine them. So if I can do all 4 of these things, add a covariate, look at one additional outcome measure, add a few observations, things that are totally within the bounds of normal practice in a lot of empirical fields across the social sciences, the odds that I'm going to find at least one significant effect is 60% now. Simple solutions to false positive publications. These are for authors. Authors have to decide the rule for terminating data collection before data collection begins and showed in the article. So no more of this, I'm going to add 10 or 20 observations. They're going to try to tie researchers' hands on that margin. you have to have at least 20 observations per cell or give some reason why you didn't. So no more of these, like, I'm going to have like 10 or 12 observations, which in lab experiments in social psychology and even some branches of experimental economics happens. Like massively underpowered analyses. And for me as an outsider to this literature, I have always asked myself, and I think that's part of the motivation for what they're doing, like, why don't these folks do like half as many experiments and have twice as big a sample size to actually say something definitive? But of course, if you're in a world of false positive results, that's the last thing you want to do. You want to have the possibility of false positives, and big samples will kill all your zero results. So you want small samples, and you live on the sampling variation and publish off that. Isn't that terribly cynical? But that's basically what they're saying in this article. Authors must list all the variables they collected. You can't just not tell us that you collected another proxy for the same thing, that ex ante was just as good as the one you published. You have to tell us all 3 of them, or 4 of them, or 2 of them. Authors have to report all the experimental conditions. These are just tying their hands against all the things they were warning about in the previous table. If you had a certain treatment in this experiment, tell us about it, show us the data. Don't exclude it without telling us about it. If observations are eliminated, if they're outliers or for some other reason, you have to report what the results are if you include the data. So this is the beginning of their robustness. If you start dropping data, you may have a good reason for doing so, but I still want to see the full sample results. Yes, you can argue and make the case for dropping them, but don't hide it. And again, same exact thing. If you run an analysis with a covariate, I want to see the unadjusted analysis. And again, there may be very good reasons for having the covariate. You make that case, but I want to see the unadjusted one. And I'm going to believe your result a lot more if it holds in both cases 5 and 6. And that's what a robustness table really is.